Nuclear Power, Actually Science, Episode 4. Chapter 1, Boiling Water. A nuclear power plant is, at its most fundamental level, a machine for boiling water. That is not a simplification for a non-technical audience. That is literally what it does. Boil water. Use the steam to spin a turbine. Use the turbine to drive a generator. Generate electricity. Coal plants do this. They burn coal to release chemical energy as heat, which boils water, which makes steam, which spins turbines. Natural gas plants do this. They burn gas to make heat, which boils water, which makes steam, which spins turbines. Oil plants do this. Geothermal plants do this. They just use the heat of the earth instead of burning anything. Nuclear plants do exactly this. The turbines, the generators, the cooling towers releasing clouds of water vapor you can see from miles away, all of that is identical to any other large power plant. None of it is nuclear. None of it is unusual. The only thing that is different is what happens in the reactor building. The only thing the reactor does is make heat, very efficiently with very small amounts of fuel, producing no carbon dioxide, and with a set of risks and challenges that are different from other energy sources. To understand those risks and challenges, you need to understand fission. Fission is the process of splitting a heavy atomic nucleus into two lighter nuclei. The fuel in most nuclear reactors is uranium-235. Uranium is a heavy element. Its nucleus contains 92 protons and, in the case of U-235, 143 neutrons, for a total of 235 particles packed into a space about 100,000 times smaller than the atom itself. When a slow-moving neutron is absorbed by a uranium-235 nucleus, the nucleus becomes unstable. It oscillates and deforms, and within about a trillionth of a second it splits into two smaller nuclei, typically something like barium and krypton, though many different products are possible. The two pieces fly apart at very high speed. That kinetic energy is quickly absorbed by the surrounding material as heat. This is where the thermal energy comes from. This is what eventually boils the water. But here is the key to why this process can sustain itself. The fission also releases 2 to 3 free neutrons. These neutrons are available to be absorbed by other uranium-235 nuclei. If each fission event causes at least one more fission event, the reaction continues. If each one causes more than one, it grows. If each one causes less than one, it dies out. This is the chain reaction, and controlling it is the central engineering problem of nuclear power. Chapter 2, The Chain Reaction. The difference between a nuclear weapon and a nuclear reactor is the multiplication factor, the average number of additional fissions caused by each fission event. In a nuclear weapon, this factor is much greater than 1. Each fission causes 2 or 3 more. Each of those causes 2 or 3 more. The reaction doubles and doubles and doubles, releasing enormous energy in microseconds. This is called a supercritical chain reaction, and it is what happens in an atomic bomb. In a nuclear reactor, the factor is maintained at almost exactly 1. Each fission causes, on average, 1 more fission, not 2, not 0.8. 1. The reaction proceeds at a steady rate, releasing a constant amount of heat, which boils a constant amount of water. This is called a critical chain reaction. Getting from supercritical to critical, getting from exponential to steady, requires slowing the neutrons down and absorbing some of them. Fission releases fast neutrons, but uranium-235 is much more likely to absorb a slow neutron than a fast one. So reactors include a material called a moderator, typically water or graphite, that slows the neutrons to thermal velocities, and they include control rods. Control rods are the throttle of a nuclear reactor. They are made of materials that absorb neutrons readily: boron, hafnium, cadmium. When a neutron is absorbed by the control rod material, it does not cause a fission. It is simply captured and removed from the chain reaction. Lower the control rods into the reactor core, and more neutrons are absorbed before they can reach uranium fuel. the multiplication factor drops below 1. The reaction begins to die out, the heat output decreases, raise the control rods partially out of the core, and fewer neutrons are absorbed. More of them reach the fuel. The multiplication factor rises toward 1 and then above it. The heat output increases. The operators of a nuclear plant constantly adjust the position of the control rods to maintain the exact level of power output the grid demands. In an emergency, if anything in the reactor behaves unexpectedly, the control rods fall fully into the core under gravity. This is passive safety. It requires no active intervention, no operator action, no electricity. Gravity pulls them in and the chain reaction stops within a few seconds. This emergency shutdown is called a scram. The origin of the term is disputed. It may stand for Safety Control Rod Axeman, a reference to an early reactor design where a person stood next to the control rod cables with an axe ready to cut them. Modern reactors do not require a person with an axe, but the principle is the same. Chapter 3: Why Chernobyl Happened. Safe nuclear reactors are designed around negative feedback. Negative feedback means that if the reactor gets hotter than intended, something about the physics of the situation automatically reduces the reactivity. The temperature rise causes a correction that brings the temperature back down. The system is self-regulating. Most commercial reactor designs have this property. If the coolant water heats up, its ability to moderate neutrons decreases, which reduces the chain reaction, which reduces the heat output. The reactor cools down. Stability is restored without any operator action. This is called a negative temperature coefficient or a negative void coefficient. When coolant turns to steam, forming voids, reactivity decreases. A positive void coefficient is the opposite. If the coolant heats up and forms steam voids, the reaction becomes more active. More reaction means more heat. More heat means more steam. More steam means more voids, which means more reaction. This is a runaway positive feedback loop. Without external intervention, without the control rods being inserted quickly enough, a reactor with a positive void coefficient at high power can escalate uncontrollably. The RBMK reactor design used at Chernobyl had a positive void coefficient under certain operating conditions, particularly at low power levels. This was a known design characteristic. Soviet engineers had documented it. It was managed through operating procedures. On the night of April 25 to 26, 1986, operators at the Chernobyl No. 4 reactor were running a safety test. They needed to determine whether, during a power outage, the spinning turbines could generate enough electricity to run the reactor's safety systems for the 60 to 70 seconds it would take for backup diesel generators to start. The test required the reactor to run at a specific low power level. Getting the reactor to that power level took longer than expected, creating a delay that left the reactor in an unstable state. When the test finally began, the reactor was in exactly the operating conditions where the positive void coefficient was most pronounced. Coolant began to boil, steam voids formed, the reactivity increased, the power began to rise. The operators recognized the problem and initiated a scram inserting all control rods, but the RBMK control rods had a design flaw. As they were inserted, the graphite tips at the bottom of the rods, which enhanced the reaction rather than absorbing neutrons, briefly increased the reactivity before the neutron-absorbing portions took effect. At the power levels now present in the reactor, this brief increase was enough. The power spiked to approximately 10 times normal operating output in about 3 seconds. The heat vaporized the coolant water, the steam pressure ruptured the pressure vessel. 2 explosions blew the top off the reactor building. The graphite moderator caught fire. The explosions were not nuclear, they were steam and chemical explosions. But the reactor core was now exposed to the atmosphere, and the burning graphite scattered radioactive material across a wide area. Modern commercial reactor designs in Western countries use light water as both moderator and coolant. If the coolant boils away, it can no longer moderate neutrons, and the reaction slows down. The positive void coefficient that caused Chernobyl is physically impossible in these designs, not prevented by procedures, impossible by physics. Modern commercial nuclear reactors in the United States, Western Europe, Japan, South Korea, and most other countries use pressurized water or boiling water designs that have inherently negative void coefficients. When the coolant heats up in these reactors, the moderation of neutrons decreases. Less moderation means fewer slow neutrons. Fewer slow neutrons means fewer fissions. Fewer fissions means less heat. The reactor cools itself down. This is passive safety. It requires no human action, no control system response, no electrical power to an actuator. The thermodynamics of the reactor do the work automatically. The Chernobyl failure mode, positive void, coefficient driving uncontrolled power increase, cannot occur in a light water reactor. Not difficult to cause, not protected against by procedure, physically impossible. The laws of thermodynamics, applied to the specific geometry and materials of a light water reactor, make it impossible. Chernobyl was a consequence of a specific design choice that Soviet engineers made and that Western reactor designers chose differently. It was not an inevitable property of nuclear power. Understanding this matters because the global energy situation in the coming decades will require serious consideration of every available low-carbon energy source. Nuclear power has real risks, primarily waste storage, construction cost, and the challenges of managing aging infrastructure. But the specific catastrophic failure mode that caused Chernobyl belongs to a reactor design that is no longer being built. The physics of boiling water has not changed. How we choose to boil it has.